Hey Math 161. So as promised, this is the video that I told you I would send you so that you can catch up on notes and we can start where we're supposed to be on Tuesday of next week after spring break. Remember, I have to stick by a specific schedule that was posted by the course coordinator, Miss Muller, at the beginning of the semester, and we have gotten a little bit behind on that schedule. So specifically, we are one lesson behind. On Thursday before spring break, we were supposed to do this lesson, logarithmic function properties and graphs. And then after spring break, the Tuesday that we come back to Math 161, we're supposed to, according to the schedule, do the lesson entitled Properties of Logarithms. But since we're about a lesson behind, I decided to make a video lecture for you on this lesson, the one we were supposed to do Thursday of last week, logarithmic function properties and graphs, so that you can watch it on your own, upload your guided notes to a link that I'm going to put on Moodle and get credit for that. And then on Tuesday when we come back, we can pick up where we are supposed to be according to the schedule. And that's important for several reasons, but mostly it's important because once we come back from spring break, we only have 3 weeks of classes and then finals. So we really don't have time to be behind, which is why we need to take the opportunity to catch up. One other thing that I wanted to say to you is I know that I said I would send this last Friday, and I did send out an email last Friday letting you know what was going on, but I did come up to Southeastern to make the video, and unfortunately, when I got here, I found out that they were waxing the floors and that I was not allowed in the building, which is really unfortunate, but apparently they were waxing the floors Friday, Saturday, Sunday, and Monday. In fact, they're still not finished. They're doing the second floor right now, which is why I am in my office creating this video and not in a classroom. So forgive my handwriting, it's harder to write on this tablet. But anyway, that's why I wasn't able to make the video until today, because I didn't even have access to the building until today. So I'm going to make this video, send it out to you, and you will have until 11:59 p.m. on Tuesday the 18th to upload these guided notes into the link that I'm going to provide on Moodle, and I will explain that in the email that I send to you when I send the link to this video, and I'll also explain like how you're going to get credit for those notes and how it's going to go into your grade and all of that. So anyway, that's enough talking. Let's go ahead and get into the lesson so that the video is not too long. Now, I teach 2 Math 161 classes. One is at 9:30 a.m. and then the other one immediately follows that at 11 a.m. Now in my 9:30 class, we got all the way through the end of the exponential function properties and graphs notes. We went all the way through number 45 and finished those notes. So the 9:30 class needs to pick up here. But my 11 o'clock class, we had a little bit more discussion and questions in that class, which is totally fine. That's great. But we only got through problem number 41 in the exponential function properties and graphs notes. So I'm going to start this lecture video by finishing up those notes, doing numbers 42, 43, 44, and 45 for the 11 o'clock class that did not get to see those. And then I'll go straight into the logarithmic function properties and graphs notes. Now, if you're in 9:30, you can just skip ahead to the portion of the video where I start these notes. Or if you'd like a refresher on numbers 42 through 45, then you can watch that as well. So it's totally up to you, but that's what I'm going to start with. Okay, so in the exponential lesson, exponential function properties and graphs, at the very end, we were discussing solving exponential equations. And so we said that if you can make your bases the same, that you can just drop the bases and set the powers equal. So let's take a look at that here. We have 5 raised to the x squared plus 8 equals 125 raised to the 2x. So I can see that my bases are not the same right now. Right now I have a base of 5 on the left and a base of 125 on the right. But I know I can write those as the same base because 125 can be rewritten as 5 to the third power. 5 to the third power is 125. So I can rewrite it like this. 5 to the x squared plus 8 is equal to 5 to the third power raised to the 2x. And then I remember that I have a property of exponents that says if you raise a power to a power, then you multiply. And I know that 3 times 2x is 6x. So then I have 5 raised to the x squared plus 8 is equal to 5 raised to the 6x. And now that my bases are the same, they're both 5, I can drop those bases and I can set the powers equal. So the power on the left is x squared plus 8, and that is equal to the power on the right, which is 6x. And immediately I recognize that as an equation that we have learned how to solve before. That specifically is a quadratic equation. And I know that when I have a quadratic equation, I first need to set it equal to 0, and then I can either factor or use the quadratic formula. So I'm going to set it equal to 0 by subtracting 6x from both sides. Okay, so of course, on this side it cancels. So I end up with x squared, I'm going to go ahead and put them in order, minus 6x plus 8 is equal to 0. And now I'm ready to either factor or use the quadratic formula. But this one's really easy to factor. I can do minus 4 and minus 2 because negative 4 times negative 2 is positive 8 and negative 4 plus negative 2 is negative 6. So this factors into x minus 4 times x minus 2, and that's equal to 0. Okay, so by the zero product property, I can set each one individually equal to 0. So I have x minus 4 equals 0 and x minus 2 equals 0. So from the first equation, I get x equals 4, and from the second equation, I get x equals 2. So for my final answer, I get x equals 2 comma 4. All right, there you go. Saving and moving on. Let's take a look at example 43. Now, example 43 has a bunch of base e's, which is great, but I cannot cancel those yet because you can only drop the bases when you have a single base on the left and a single base on the right. And that's not the situation that I have here, because if you take a look at the left-hand side, I have 2 bases of e. I need a single base of e on the left-hand side before I can drop it. And so what I'm going to have to do is use some of my exponent rules to simplify the left-hand side so that I only have 1 base of e on that side. So the first thing I see is that I have a power raised to a power here. It's e to the 4th, and then that's raised to the power of x. And I know that when I have a power raised to a power, I multiply. So this can be e to the 4x times e to the x squared is equal to e to the 12th. So I've used one exponent rule that we learned at the beginning of this lesson, but I'm going to have to use another one because I still don't have a single base of e on the left-hand side. But I have another exponent rule that says if you multiply, which is what that dot indicates, if you multiply 2 like bases, you can add their powers. So I can take these 2 powers and add them together. So this becomes e raised to the x squared plus 4x, and then that's equal to e to the 12th. Well, now that I have a single base of e on both sides, I can drop it because the bases match. And when the bases match, you can drop them and you can set the powers equal. So we have x squared plus 4x is equal to 12. And again, I have a quadratic, and I learned how to solve a quadratic in the previous unit. I want to set it equal to 0 and then either factor or use the quadratic formula. So I'm going to set it equal to 0 by subtracting 12 from both sides. So of course it cancels on that side. That was the goal. So I have x squared plus 4x minus 12 is equal to 0. Now, again, this one is pretty easy to factor because if we do, let's see, positive 6 and negative 2. Positive 6 times negative 2 would give me negative 12, and positive 6 plus negative 2 would give me positive 4. So we want to do positive 6 and negative 2. So we'll have x plus 6 and x minus 2 equals 0. By the zero product property, you can set each factor individually equal to 0. So we have x plus 6 equals 0 and x minus 2 equals 0. So we get x equals negative 6 and x equals 2. And there's our final answer, x equals negative 6 comma 2. Now, I just want to remind you that the beauty of watching a video lecture versus seeing it in class is that anytime you need to hear me give an explanation again, all you have to do is back the video up a little bit and you can listen to it again. And also you can pause the video at any time if you need more time to write something down or maybe think through something. So feel free to pause and play the video as much as you need in order to make sure that you understand everything thoroughly. But that's number 43. So for now, let's go on to number 44. So number 44 is sort of a tricky question, but once I show you how to do it, it's pretty easy. It says if 4 to the x is equal to 7, what does 4 to the negative 2x equal? Well, they're wanting you to use an exponent rule here, but they want you to use it backwards. So let's look at 4 raised to the negative 2x. What we know from our exponent rule is that if you raise a power to a power, you can multiply those together. So since negative 2, and x are multiplied together, we can use that rule in reverse. We can say, well, since negative 2 is multiplied by x, it must have originally been negative 2 raised to the x. So we want to rewrite it like this. 4 to the negative 2 raised to the x. Another way we could rewrite it is to switch those as 4 to the x raised to the negative 2. And we know we can switch them because negative 2 times x is the same thing as x times negative 2. But the second way that I wrote it, the 4 to the x raised to the negative 2, that is so much more helpful because here's the thing. I know from the beginning of the problem that 4 to the x is equal to 7. So I can replace 4 to the x with a 7. So 4 to the x raised to the negative 2 becomes 7 raised to the negative 2. And then I know from another rule of exponent that we went over at the beginning of this lesson that a negative exponent actually indicates that that factor is in the wrong position. It should be in the denominator. So 7 to the negative 2 can be rewritten as 1 over 7 squared. And I know that 7 squared is 49. So I have 1 over 49. And that is the answer that we're looking for. Okay, so you make sure you have that written. I'm just going to double check a few things really quickly. Okay, looks like we're all good. So that was 42, 43, and 44 from our exponential notes. And we have one more example from our exponential notes, and that is example 45. And as always, all of my examples in my notes come straight from Pearson. So it says, suppose that g of x is equal to 4 raised to the x plus 2. And then they asked me 2 questions. The first question said, they actually asked me 4 questions, 2 questions in part A and 2 questions in part B. So part A said, what is g of -1? And what point is on the graph of g? Well, everybody should know at this point in college algebra how to calculate g of -1. To calculate g of -1 means to plug -1 into the g function. Okay, so you're going to write that as 4 raised to the -1 plus 2, which is the same thing as 1 over 4 plus 2. Now at this point, I want you to take your calculator and I want you to type 1 over 4 plus 2. And then it's going to give you 2.25, but if you do second F to D and second ABC, it'll tell you that that's 9 over 4. So 9 over 4 is your first answer. That's what you get if you plug -1 into the g function. Now, if you have calculator issues, I completely understand. You can catch me after class, you can send me an email, or you can come see me during my regularly scheduled office hours from 1 p.m. to 3 p.m. Monday through Thursday, and I'll be happy to show you how to do those fractions in the calculator. The math tutors can also help you with those, and they're available from 8 a.m. to 5 p.m. Monday through Thursday, and also 9:15 a.m. to 12:15 p.m. on Fridays in Fayard 309. So if you don't know how to use your calculator to do these fractions, definitely use some of those resources I just mentioned and make sure that you are on top of it. So that's the answer to the first question. What is g of -1? 9 over 4. Now the second question says, what point is on the graph of g? Well, what they're wanting you to understand is that what you plug in is your x value, and what you get out is your y value. So a coordinate point has an x value and a y value. Well, what you plugged in was your x, and what you got out was your y. So the point that corresponds to that information is the point -1 comma 9 over 4. So this would be your second answer for part A. All right, now let's take a look at part B. It says, if g of x is equal to 66, what is x? So they're saying here, well, if the y value is 66, what is x? And then, of course, we'll be able to make a point from that again because we'll have both an x value and a y value. Now, they didn't ask us to find g of 66, so we're not plugging 66 in. They asked us to find x if g of x is equal to 66. So we're going to take the function for g of x, which is 4 to the x plus 2, and we're going to set it equal to 66. So we have 4 raised to the x plus 2 is equal to 66. And now we're going to take this equation and we're going to try to solve it for x. So the first thing we're going to do is subtract 2 from both sides. So when we do that, we get 4 raised to the x is equal to 64. And now we're going to solve these equations like we just solved numbers 42 and 43. We learned that if we can make the bases the same, we can drop the bases and set the powers equal. Well, 4 and 64 can be written as the same base because 64 is the same thing as 4 to the third power. So I can rewrite this 64 right here as 4 to the third power. So I have 4 to the x is equal to 4 to the third power. And now that the bases are the same and I only have one base on each side of the equal sign, I can drop the bases and set the powers equal. So that's really easy. I get x equals 3, and that is my first answer. Now remember, my second answer is the point that corresponds to this information. And again, we know that a point or a coordinate point contains an x value and a y value. So up here, we said that the y was the output, so the y is 66, and then we figured out that the x was 3, so our corresponding point is 3, 66. Okay, so for my 11 o'clock class, that finishes up your exponential function properties and graphs notes. And now we're going to jump right into the logarithmic function properties and graphs notes. So it says, do you remember when we learned to take the inverse of a function in section 6.2? Now, I didn't label the section 6.2, but I did label it like composite and inverse functions or something like that. But in a few lessons ago, still in Unit 3, we learned how to take the inverse of a function. So that's what we're going to do here. Example 1, we're just remembering what we did in a previous lesson. It says find the inverse of the one-to-one function f of x equals 3 over x minus 2. So if you'll remember with me, step 1 was to rewrite the function with a y. So we'll write it as y equals 3 over x minus 2. Step 2 was to switch x and y. So we have x equals 3 over y minus 2. Now step 3 was to take and solve what you got in step 2 for y. So we're going to solve for y. Okay, so if I have x equals 3 over y minus 2, and I want to solve for y, the first thing I'm going to do is get rid of that fraction by multiplying both sides by the denominator. So I'm going to multiply both sides by y minus 2. Let me move my screen down a little bit. Okay, so on the left-hand side, nothing cancels. I'll just write it as x times y minus 2. And on the right-hand side, the y minus 2's cancel here. And so I'm just left with a 3. Now, I've still got to figure this out, but I think I'm going to go ahead and distribute because that might make life a little easier. So I'll distribute that x. So x times y is xy. Negative 2 times x is minus 2x, and that's equal to 3. So I stop here and I remind myself that y is what I'm trying to solve for. So I only have one term with y in it, so I need to try to isolate that term. So I'm going to do that by adding 2x to both sides. Okay. So I get xy equals 2x plus 3. Now I've almost done it. I've almost isolated the y. The only thing I have left to do is divide both sides by x because x is currently being multiplied by y. So I divide both sides by x. So I get y equals 2x plus 3 over x. Okay, so that's my inverse. I'm going to come up here and write my final answer with inverse notation instead of with a y. That's sort of my step 4, is to write it with inverse notation. So I can say f inverse of x is equal to 2x plus 3 over x. All right. So that was just a little walk down memory lane, just a way to remind you how to find inverses, the 4-step process for finding inverses, because this lesson on logarithms is going to build on that. All right, so let's see what's next. So it says in section 6.2, we learned that if a function is 1, 2, 1, there's your blank there. We learned that if a function is 1 to 1, then it has an inverse. So now I want you to think about the exponential function that we learned in the last lesson. This was it. This was the parent function that I gave you for the exponential function. We learned this function, and I told you to put this in your memory, in your library of functions, and remember this as the parent function for an exponential graph. So we said that it curves this way, it's increasing. We said that it has a horizontal asymptote at y equals 0. And we said that it has 3 key points, -1, comma 1 over a, 0, 1, and 1, comma a. So now let me ask you this question. Is this function 1 to 1? And how do you know? Well, yeah, the function is definitely 1 to 1 because it passes the horizontal line test. Remember, that was one of the first things we learned in Unit 3. If you are looking at a graph and that graph passes the horizontal line test, then you know that that function is 1 to 1. So this is the parent function for an exponential graph. And I'm looking at it and I can tell you right now that if I drew 1,000,000 horizontal lines, every single one of those lines would only cross or intersect the graph one time. Therefore, it passes the horizontal line test. And if it passes the horizontal line test, then it's 1 to 1. So let's take this space to answer the question. Is the exponential function 1 to 1? We're going to say yes, it is 1 to 1. And when it says, how do you know? The answer is it passes the horizontal line test. So now let's build on this. Since we know that the exponential function parent graph passes the horizontal line test and is therefore 1 to 1, then we have to be able to take the inverse. Because the next thing that we learned was that all 1 to 1 functions have inverses. In fact, a function doesn't have an inverse unless it's 1 to 1. So let's see what's next. Since the exponential function is 1 to 1, there's your blank again. Let's go ahead and fill that in. 1, 2, 1. Okay. Since the exponential function is 1 to 1, then it must have an inverse. So let's try to find the inverse. Let's take a really basic function. Example 2 says, find the inverse of the 1 to 1 function f of x equals 2 to the x. Okay, let's try to do those same 4 steps that we did on the rational function in example 1 a minute ago. So step 1 was to change the f of x to a y. No problem. Y equals 2 raised to the x. Step 2 was to switch x and y. Again, no problem. X equals 2 to the y. Step 3 was to take step 2 and solve for y. But you see, this is where we have an issue. Because how do I get y out of the exponent position? Now, some of you are thinking, and some of you are thinking ahead, and you're thinking, well, couldn't I take like the y root of both sides? Sure, but y would still be in the exponent position. It'd be in the root. So with our current knowledge, what we have currently learned up to this point in Math 161, we have absolutely no way of getting that y out of the exponent position. And therefore, we have no way of finding the inverse of this exponential function, even though we know that the inverse has to exist because we know from the graph passing the horizontal line test that it does exist. So that's why logarithms are created. If you want to know the point of logarithms, why someone created logarithms, logarithms were a way to rewrite. So let me rephrase this. Hold on. Let me add a word in there because this is important. Logarithms were created as a way to rewrite exponential functions so that we can take their inverses. Because before logarithms, we had no way to take the inverse of an exponential function, even though we knew that it existed. So what we're going to do is actually pause this example here because I currently haven't taught you how to do that. So I'm going to go through the lesson and teach you about logarithms. And then later on down the lesson, once we learn how to use logarithms to rewrite exponentials so that we can take the inverse. We'll come back to example 2 and finish it up. But for now, let's keep going so we can learn a little bit more about logarithms. So again, this is why we have logarithms. So here's your blank here. Okay, so we're going to say logarithms. There we go. Hold on, I'm spelling things wrong. You'll forgive me. There we go. Okay, so logarithms are a way to rewrite exponential functions so that the inverse of an exponential function can be taken. That's what I was talking to you about a minute ago. So this came from the book that we use for this course. But if you have a logarithmic function with a base of a, so see, this is how we write a log, L-O-G, and there's the base of a. You read this as y is the logarithm with base a of x. But here's what you need to know. This is the important part right here, okay? This right here is how we rewrite logarithms as exponentials and exponentials as logarithms. So if you have y equals log base a of x, okay, that is equal to or the same as x raised, or I'm sorry, x is equal to a raised to the y power. So you can rewrite this logarithm as this exponential, or you can rewrite this exponential as this logarithm. And actually the very first types of problems, oops, skipped a page. The very first types of problems that you're going to see when you go to do this Pearson assignment, all they're going to ask you to do is rewrite the logarithms as exponentials and the exponentials as logarithms. Literally all you have to do is rewrite them. You're not solving anything. So we're going to see one such example like that in example 3. So before we do that, let's go ahead and write our little rule that we wrote a second ago. So y is equal to log base a of x is the same thing as a raised to the y equals x. Okay, so your first example is going to say change or rewrite each exponential statement as the equivalent statement involving a logarithm. So they're going to give you an exponential statement like you see in A, and they're going to ask you to rewrite it as a logarithm. So we have 1.2 raised to the third power is equal to m. Okay, so let's look at how this was rewritten. Okay, they gave you this form, the exponential form. So whatever's in the position of x goes inside the log. The base of the exponent becomes the base of the log, and the exponent is what it's equal to. Okay, so let's see, I wrote on it, hold on. Okay, so you're going to write this as, let's see, 1.2. Nope, you're not, just kidding. Try that again. You're going to write this as 3 is equal to log base 1.2 of m. So you can kind of think of it as a circle, if you will. So it's the exponent, that's what it's equal to, is equal to log of m, and the base is 1.2. So 3 is equal to log base 1.2 of m. It's going to take some practice, but definitely take a minute to look at it. If you need to pause the video, try it again. It's really just memorizing how to write one form into the other form. But let's do some more practice first. So we have log base 1.2 of m equals 3. Let's try it again. Okay, so this one says e to the b is equal to 9. Okay, so remember our rule. We start with the exponent, that's up here. Okay, we set it equal to, and then it's like our little circle. Okay, so it's log of 9 with a base of e. Okay, so Let's talk about this though. This is the right answer. You could enter this in as your answer to Pearson, just like you could enter this in right here as your answer to Pearson, okay? But log base E, we're going to talk about this on the next few slides. Log base E is so important that it has a special name, okay? Log base E can also be written as natural log. So you could leave, let's see, I meant to write that on the other page. Let's see if it'll let me copy it. Hold on. Look at all my tech skills. I'm just kidding. Okay, here we go. Log base E is the same thing as the natural log. You see, log base E has so many real life applications that it can also, that like people came up with a special name for it. And so it can now also be written as natural log. So you could write this as B equals log base E of 9, or you could write it as B equals the natural log of 9. By the way, that's ln, not in. People always think it's in, but it's ln. Anyway, both of these are equivalent ways to write that, and then they would both be correct. All right, so let's try it one more time. We are learning how to write exponentials as logarithms. Okay, so remember the exponent is what we start with. So let's circle that. So it's the exponent is equal to, and then we do a little circle, okay? So it's log of 24 with a base of a. So that's log base a of 24. So 4 equals log base a of 24. You could also write that as with any of them, as log base a of 24 equals 4. That's the same thing. Okay, but anyway, here's your answer. And the way that I remember it, I do the little circle like I'm doing with you guys, but also whatever the base of the exponent is, that is the base of your log. So in the original, it's a to the 4th. So a is the base of the exponent 4. And so when I rewrite it in its logarithmic form, a is also the base of the log. Okay, so there's 3 examples for you of rewriting something that is given in exponential form to its equivalent logarithmic form. So now in the next example, we're going to do the opposite. So basically the same directions, except they're going to give it to you in the logarithmic form and you have to rewrite it in its exponential form. Now, to me, these are a little bit easier, if I'm being honest with you, because these can be done with a circle as well. So remember, this is the base. You're basically doing the opposite of what you did before. Here we have log base a. A is the base of 4 equals 5. So it's a raised to the 5th power set equal to what's inside. So let me say that again. A raised to the 5th power set equal to what's inside. And there you go. That's how you rewrite an exponential, or excuse me, a logarithm as an exponential. Base raised to the other side of the equal sign equals what's inside. Again, for this one, that would be a raised to the 5th is equal to 4. You'll have several like this as well. So let's try it again. Okay, this is that special note I was talking about. Log base e of x is so special that it gets its own separate name, which we call natural log of x. So if you see natural log of x, or ln of x, again, that's an L, not an I. If you see ln of x, you can just rewrite it as log base e of x and vice versa. Okay, so here we have log base e of x, or log base e of b, excuse me, equals 3, negative 3. And our goal is to rewrite this in its exponential form. We're not solving anything. We are just translating it. It's sort of like exponential is one language and logarithm is another language, and you're just translating it just as you would translate from English to Spanish or Spanish to French. We are just translating this logarithmic equation into its equivalent exponential equation. So I'm going to do the little circle thing again. Base raised to the other side of the equal sign set equal to what's inside. So it would be e raised to the negative 3 set equal to b. Okay, and that would be it for example 4b. All right, we have two more where we're rewriting the logarithmic form as the equivalent exponential form. So let's do it again. We have log base 3 of 5 is equal to c. So we start with the base, we raise it to what's on the other side of the equal sign and set it equal to what's inside. So 3 raised to the c is equal to 5. Again, feel free to pause the video at any time or rewind it if you feel that you need to hear an explanation again. But let's look at D. Now remember our special note. Log base e of x is so special that it gets its own separate name, natural log of x. So if you see natural log of x, you can just rewrite it as log base e of x and vice versa. So here in example 4D, we have natural log of 16 equals x. So it's going to be hard for me to rewrite this if I can't do my little circle trick. So I'm going to rewrite natural log as log base e so that I can actually see the base and do my little circle trick. So this is log base e of 16 is equal to x. So I start with the base, raise it to what's on the other side of the equal sign, and set it equal to what's inside. So e raised to the x is equal to 16. Okay, so there are examples 3 and 4 where you have to rewrite exponentials as logs and then rewrite logs as exponentials. Just be prepared that you will have several of those in your homework when you go to do this assignment. Also, as a side note, one other benefit that you could take advantage of since you have to watch this lecture in a video versus in class, you're welcome to like stop after each example and then go try those homework problems. So like if you wanted to now, you could pause the video, jump over to Pearson, and just try the homework problems where you have to rewrite exponentials as logs and vice versa. And then once you master those, you could come back and watch the next portion of the video if that's helpful to you. So take advantage of that if you think that that would be helpful. But for now, we'll go on. So it says, find the exact value of the following logarithms. So we're going to do this by rewriting logs as exponentials. So we're going to use what we just learned in example 4 to actually simplify these logarithms. So, or another way to say that is find the exact value of them. So A says log base 2 of 16. So what we're going to do is set that equal to x. I want you to pretend there's an equals x at the end of it. And now we're going to look at this as an equation. We're going to try to solve it. So the way that I'm going to solve this equation is I'm going to rewrite it as an exponential, just like I did in example 4. So I'm going to circle the base. I'm going to say 2 raised to the x is equal to 16. So let me write it that way. 2 raised to the x is equal to 16. Now I know how to solve that. I know how to solve that from my lesson on exponentials. If I can write the bases the same, I can drop the bases and set the powers equal. Well, 16 can absolutely be written as a base of 2. In fact, 16 is equal to 2 to the 4th. So I can rewrite this as 2 to the x is equal to 2 to the 4th, and then I can drop the bases and set the powers equal. So I have x equals 4. And so you would just type in 4 as your answer to Pearson. Okay, and we're going to do several of these. So if you need to hear the explanation again, feel free to rewind it or whatever. But we're going to look at example B and do this again. Okay, so same as last time. We're going to set this equal to x. And then we're going to solve for x by rewriting this. So 3 raised to the x and set equal to what's inside. So 3 to the x is equal to 1 over 27. Okay, so I know that 1 over 27 can be written as 27 to the negative 1. But while that's true, totally true, I think it would be easier to think of it like this. I need the bases to both be 3 so that I can drop them. And 3 to the third equals 27. So I know that 1 over 27 is the same thing as 1 over 3 to the third power. Okay, and so using my rules of exponents, I can rewrite that. Oops, not like that. Hold on. I can rewrite that as 3 to the negative 3. Okay, so what I've figured out here is that 1 over 27 can be rewritten as 3 to the negative 3. So I'm going to rewrite it like that, because then I have 3 to the x is equal to 3 to the negative 3. And once the bases are the same, and I only have 1 on each side, I can drop the bases and set the powers equal. So then I just get x equals negative 3, and I'm done with that one. So that was easy. Okay, let's go to the next one. All right, so starting the same way, log base 1/2 of 32. So I'm going to set it equal to x, because that's what I always do, and then I solve for x, and that's how I get my answer. So I'm going to circle the 1/2, raise it to the other side of the equal sign, set it equal to what's inside. So we have 1/2 raised to the x is equal to 32. Okay, so I'm going to have to rewrite both of them this time. But I know that 1/2 can be written as 2 to the negative 1. Okay, so this can be written as 2 to the negative 1 to the x equals, and then also 32 can be written as a base of 2 as well. If you don't believe me, try it in your calculator. But 32 is the same thing as 2 to the 5th power. Okay, so if I raise a power to a power, I multiply. So this is essentially 2 to the negative x is equal to 2 to the 5th. And once I have the same base on both sides, I can drop the bases and set the powers equal. So of course I have negative x equals 5. And dividing both sides by negative 1, I have x equals negative 5. So negative 5 would be my answer for this one. Okay, let's look at another one. All right, so we have log base square root of 6 is equal to 36. Oops, looks like I moved that on accident. Hold on. All right, so that's okay because I forgot to set it equal to x, which we need to do so we can do our little circle trick. So we'll set that equal to x, and square root of 6 raised to the x set equal to what's inside. So I have square root of 6 raised to the x set equal to what's inside. Now here I'm going to have to reach back in my memory from some things that we did in a previous unit. So previously we learned that the square root is the same thing as the 1/2 power. So what that tells me is that the square root of 6 can be rewritten as 6 to the 1/2 power. So this is the same thing as 6 raised to the 1/2 power raised to the x. And then of course 36 is 6 squared, I know that. So I can write this as 6 squared. So I'm pretty close to being able to drop my bases because they're the same. I just need to use my exponent rule here to multiply those two, because when I raise a power to a power, I multiply. So that would be 6 raised to the 1/2 x is equal to 6 squared. Okay, so I can drop my bases now because they're both 6. And then I can say 1/2 x is equal to 2. Solving that equation, you can either divide both sides by 1/2 or multiply both sides by 2. Either way, if you do your arithmetic right, you get that x equals 4. So 4 would be your answer for that one. Okay. Right, so there's part D, and I think we have one more of these because these are somewhat difficult, and so I just wanted to make sure that everybody had lots of examples of them so that you were adequately prepared for your homework. But let's take a look at this one. Now, I am going to set it equal to x, but remember, it's hard to use your little circle trick to rewrite this logarithmic expression as an exponential expression when it's written as natural log instead of log base e, because you can't see your e or whatever your base. So I'm going to first rewrite this instead of natural log. I'm going to put log base e of the cubed root of e is equal to x. Now that it's written like that, which we have done before, we're going to go ahead and use our little circle trick to rewrite this logarithmic equation as an exponential equation. So we have e raised to the other side of the equal sign set equal to what's inside. So that's going to be, I'm going to write it up here. It's going to be e raised to the x is equal to the cubed root of e. Now I know that the cubed root is the same thing as the 1/3 power. So that can be rewritten as e to the x is equal to e to the 1/3 power. And once the bases are the same, we can drop the bases and just set the powers equal. So we get that x equals 1/3. And there you have it. All right, so whenever you get to the homework and the directions say find the exact value of the following logarithms, I want you to set the expression equal to x, rewrite it as an exponential using the circle trick, and then solve that little exponential equation. So if you'd like to do that, you can go ahead and do it now, but otherwise, we will just keep going. It is starting to thunder and lightning outside, just so y'all know. So if you hear crazy noises, that's what it is. Hopefully the internet will hold out to the end of this video. But anyway, all right, so we've done through example 5. And continuing on, I'm actually going to turn the light on in my office because it's gotten kind of dark outside. Okay, so continuing on, it says, now let's talk about the graph of a logarithmic function. To help you visualize the graph, let's first fill in some blanks. So logarithmic functions are useful because they allow us to find the, here's your first blank, to find the inverse of exponential functions. So we've really been talking about that this whole time. The purpose of the purpose of logarithms is to have a way to rewrite exponentials so that we can find their inverses. Now, from section 6.2, which was the inverse section, we also know that the graph of an inverse function is the graph of the original function reflected about the line y equals x. So we learned that already in this unit when we were discussing inverses in that set of guided notes. What we learned is that if you graph a function and its inverse on the same coordinate plane, they're going to look like reflections of each other over the line y equals x. And just remember, my lines are going to be terrible on here. Y'all forgive me. It is so hard to write on this little tablet. Hold on. Let's see. Let me move it down so I can write it a little straighter. Okay, let's try it. So y'all forgive me on the graphing section, okay? But here's your coordinate axes. Y'all pretend like that's real straight. Anyway, the line y equals x looks like this. Let me see if I can move it. The only thing is it just goes through 0, 0. Okay, so this is the line y equals x. And if you graph an original function and its inverse on the coordinate plane, those two graphs are going to look like reflections of each other over the line y equals x. So that's what we learned in a previous lesson. Well, we know that the graph of an exponential function looks like this. So there's your first blank there, exponential. We know that the graph of an exponential function looks like this. How do we know that? We know that because we studied it in the last lesson. We memorized it. We added it to our library of functions. That is what the parent function for an exponential looks like. Remember, we called it f of x equals a to the x? So the graph of a logarithmic, there's your blank here. So the graph of a logarithmic function has to look like this. Think about it. Y'all, this is connecting all of the things that we've learned in Unit 3 thus far. If you're tired of watching this video, which I totally get it, pause, go take a break, come back, do what you got to do. But if you miss everything else that I tell you in this video, please don't miss this concept. Exponentials and logarithms are inverses of each other. So if this is your exponential function right here, this blue one, it has these three key points: -1, 1 over a, 0, 1, and 1 over a. We learned that in the last lesson. But in the lesson before that, we learned that in an inverse function, x and y literally switch places. So if these are your three key points on an exponential function, then your three key points on a logarithmic function are going to be the reverse of that. Instead of -1, 1 over a, you're going to have 1 over a, -1, because that's what an inverse does. Instead of 0, 1, you're going to have 1, 0. Instead of 1a, you're going to have a1, because that's what an inverse does. And look, there's that line y equals x that we talked about. You can see that the exponential is a reflection of its inverse, which is the logarithmic. So this blue graph is your exponential graph per se, your exponential parent function, and this red graph is your logarithmic function. So let's talk about the blue one, y equals a to the x. Okay, first thing you need to know is that it has three key points. Okay, definitely make sure you write this with me because this is vital that you understand this. The three key points are -1, 1 over a, 0, 1, and 1, a. Those are the three key points of every exponential. It has a horizontal asymptote at y equals 0. Its domain is -infinity to infinity. Every exponential ever is going to have a domain of -infinity to infinity. And then its range is going to be like dependent on where that horizontal asymptote is. So the range for this one would be 0 to infinity. Okay, now let me switch to red and let's talk about the red graph, which is the inverse. It's the logarithmic function. So we have y equals log base a of x. Okay, it also has three key points. All right, its three key points are a, 1. Why? Because the other one had 1, a. And when we take an inverse, we switch places. Then instead of 1, 0, or instead of 0, 1, excuse me, it's going to be 1, 0. Then instead of -1, 1 over a, it's going to be 1 over a, -1. Because that is what an inverse does. It switches those x, y positions. So here are your three key points for the exponential. Here are your reversed three key points for the logarithmic. Okay, it does not have a horizontal asymptote. It is the opposite of that because it's the inverse. So instead of a horizontal asymptote, it has a vertical asymptote at x equals 0. This makes sense because x and y switch places. And in the exponential, it had a horizontal asymptote at y equals 0. So that's going to switch places on the inverse, and it's going to have a vertical asymptote at x equals 0. Okay, continuing. Let's talk about the domain and range. Well, just like every exponential in the entire world has a domain of -infinity to infinity, every logarithmic in the entire world has a range of negative infinity to infinity. The domain is going to be wherever the vertical asymptote is to infinity or to negative infinity. So this one would be 0 to infinity. Y'all, I told you they were inverses. Look at this. When we discussed our inverse section, we talked about how not only do x and y switch places, which is why you have the 3 key points over here and the 3 key points over here, but also in inverses, domain and range switch places. And that can be clearly seen when you're looking at these two parent functions. So I hope you got all that. Again, if you need to listen to the explanation again, just rewind the video. But for now, we'll just keep going. Okay. So next up, it says, now remember, the logarithmic function can be vertically stretched, vertically shifted, that is up or down, horizontally shifted, left or right, reflected over the x-axis, or reflected over the y-axis, just like any other function. So for example 6, I want you to consider the parent function. Okay, so here's your parent function here. Consider the parent function, f of x equals log base a of x, where the base is bigger than 0 and a is not, or yeah, base is bigger than 0 and isn't 1. Give the transformations for each of the following functions. Okay, so there's your parent function. So I want you to look at it. If there's a negative on the outside, what do you think that is? Well, that's a reflection about the x-axis. So reflected about the x-axis. If you will remember with me, I did this exact same thing with exponentials in the last lesson. This whole example, example 6, has parts A through H. What I'm doing in this example is showing you what transformations look like on logarithmic functions. So what I'm telling you in example A is that if you look at a logarithmic function and there is a negative on the outside, that indicates a reflection about the x-axis. Okay, so let's look at another one. F of x equals log base a of negative x. So now I'm saying, what if the negative is on the inside? Well, that's a reflection about the y-axis. So this one has been reflected about the y-axis. Okay, let's take a look at C. All right, C's got a 4 multiplied onto the front. We've talked a lot about this. A 4 multiplied onto the front, really any number multiplied onto the front like that, is a vertical stretch or compression. If the number is bigger than 1, then we consider that a vertical stretch. If the number is a proper fraction, like something between 0 and 1, then we consider that a vertical compression. But 4 is definitely bigger than 1, so this would be a vertical stretch by a factor of 4. So we're going to say that this function was vertically stretched by a factor of 4. That's a vertical stretch by a factor of 4. That's what that would look like on a logarithmic function. Okay, so let's take this one. F of x equals log base a of x plus 4. Well, since the plus 4 is inside of the parentheses, I know that that indicates a shift to the left or the right. And since it's plus 4, I'm going to remember from my lesson on transformations that that would be a shift to the left 4. So I'm going to say that this function has been vertically shifted. I'm sorry, horizontally shifted, excuse me, because it's left or right. Let's fix that. I apologize. We're going to say horizontally shifted to the left 4 units. Okay, so that's what a horizontal shift, specifically to the left 4, would look like on a logarithmic function. All right, continuing on, we have log f of x equals log base a of x plus 4. But this time the plus 4 is not inside of a set of parentheses, and therefore we consider it on the outside. So that would mean it was an up or down shift. So since it was plus 4, we would say that it was up 4. So this one would be vertical. I said the wrong word last time. We had to change it. But this one would be vertically shifted up 4 units. So this one is vertically shifted up 4 units. All right, let's take a look at another transformation. So this one's back inside of those parentheses, and since it's inside of those parentheses, we know that it's going to be a horizontal shift, either to the left or to the right. But since it's -7, we should say that that's to the right. So this one would have been horizontally shifted to the right 7 units. Okay. And up next, we have part G, which says f of x equals log base a of x minus 7. Again, very similar to part F. The difference is the parentheses. But since the parentheses are not present, we assume that the -7 is on the outside, which would indicate a vertical or up or down shift. And since it's -7, we would say down 7. So this would be vertically shifted down 7 units. Okay, so this one was vertically shifted down 7. This one was horizontally shifted to the right 7. This one was vertically shifted up 4, horizontally shifted to the left 4, and then this was a vertical stretch of 4. Okay, so now you have a good idea of all the different types of transformations that you can see on a logarithmic function. And so we're going to take a look at part H, which is going to put all of this together. Now, this part right here is problematic. Remember that inside the parentheses, or if you were doing an exponential function, you could consider the exponent position. It can't be written backwards. So if we're going to accurately see the transformations that have occurred to this function, then we need to write it in the proper order. And if x is negative, we need to factor that negative out. So let's go ahead and do that now. So we have f of x is equal to -8 log base a of, now I'm going to write that in the proper order. Instead of 3 minus x, I'm going to say -x plus 3, and then I'm going to close the parentheses and put plus 2. But since we have this negative on the outside of the x, we have to assume that it has already been distributed into those parentheses, and we need to pull it out. So this would be -8 log base a of, now I'm going to pull a negative out, and if I pull a negative out of here, then both of these change signs. So the -x becomes +x, and the +3 becomes -3. So now that we've put the inside of those parentheses in the correct order, and we've factored out that negative that was already distributed, we can accurately see our transformations. So let's take them piece by piece. Okay, this negative right here, that indicates an x-axis reflection. So must have had an x-axis reflection. I'll write that here. Okay, it's good to have these things labeled for note-taking purposes. But then this negative here on the inside of the parentheses, that indicates a y-axis reflection. Okay, so this must have had both an x-axis and a y-axis reflection. Now there's a couple more we've got to talk about because we also have this 8 here. Now that 8 is being multiplied onto the front of the logarithm, so we would say that that is a vertical stretch by a factor of 8. So vertical stretch by a factor of 8. Okay, then we also have the -3 that's right here, and that would be a shift to the right 3 units. So we're going to say shifted right 3. And then this +2 on the end indicates that it was shifted up 2. So that's kind of a culmination of all the different transformations that we saw in parts A through G. We have an x-axis reflection, a y-axis reflection, a vertical stretch by a factor of 8, a shift to the right 3 units, and a shift up 2 units. As always, if you have any questions on that, shoot me an email, come see me in my office, stop me after class. But those are the different transformations that you could see when it comes to logarithmic functions. So let's look at another problem from Pearson, because as always, my problems always come from Pearson. Let's take a stab at example 7. So it says, find the domain and range of each function. So they're going to give you a function like this. It says g of x equals the natural log of 1, or excuse me, x minus 1. So I've not taught you how to find the domain of logarithms yet. So on the side of your paper, I need to give you a rule for finding the domain of logs. So here's your rule for finding the domain of logs. Now, because the parent function for a logarithm has a vertical asymptote at x equals 0, the domain is going to be found by taking the inside of the log. So you're going to take the inside of the log and set it greater than 0. And then, of course, you're going to solve that. So we'll say take the inside of the log, set it greater than 0, not greater than or equal to. That's what we do for square root functions. But we just want to set it greater than 0 and then solve. And that's how we find the domain of logs. Okay, so there's our rule. And now that we have that rule, we're going to come back to part A, where they give us this g of x function, and we're going to see if we can find the domain and the range. So let's find the domain first. Okay, the domain we know is found by taking the inside of the logarithm and setting it greater than 0. So the inside of this logarithm is x minus 1. So I'm going to take x minus 1 and set it greater than 0. Then I add 1 to both sides, so I get x is greater than 1. All right, and that is my domain. Now, I'm not sure how they're going to ask you to write it. So if they ask you to write it in set builder notation, you would say x such that x is greater than 1. Okay? But x greater than 1 in interval notation, because they could ask you for it in interval notation, x is greater than 1 means it starts at 1 and goes to infinity. So that would be 1 to infinity. Okay, so that is how we find the domain of a logarithm. Now the range is incredibly easy because it does not matter what your logarithm is, the range is always negative infinity to positive infinity. So depending on how they ask you for it, it's either going to be all real numbers, okay, or if in interval notation, you would put negative infinity to infinity. But the nice part about logarithmic functions is that you never have to think about the range at all. The range is always negative infinity to positive infinity or all real numbers. Okay, so there's your first example, example 7a, for domain and range of a logarithmic function. So let's take a look at another one. This logarithmic function looks much more complicated than the logarithmic function that was given to us in part A. So this one says h of x is equal to 3 minus 2 log base 4 of x over 2 plus 5. Now I gave you such a complicated one on purpose. Remember, all we are asked to do here is find the domain. Okay, that's our first thing to find. And then we are asked to find the range. But let's go back and take a look at our rule for finding the domain of logs. All you have to do is take the inside of the log, set it greater than 0, and solve. So if I'm taking a closer look at this problem, the only thing that's inside of the logarithm is x over 2 plus 5. The 3 and the minus 2, like all of that is outside of the logarithm. So I don't care about it, because the only thing that I need to find the domain of a logarithm is the inside of that logarithm. So the only part of this that I care about, since I was asked to find the domain, is the x over 2 plus 5. Oops, I didn't change it back. Hold on. Let me erase this first. There we go. All right, let's try that again. So we're going to have x over 2 plus 5 is greater than 0. Okay, I'm going to see if I can get this to fix. There we go. That's what I wanted. Okay, so you can start solving that if you know how to. But the first step would be to subtract 5 from both sides. So you would have x over 2 is greater than negative 5. Okay, and then we would get rid of that denominator of 2 by multiplying both sides by 2. So we would have x is greater than negative 10. And that's it. That's the domain. So if they asked me for the domain in set builder notation, I would say x such that x is greater than negative 10. And if they asked for it in interval notation, I would say negative 10 to infinity. Okay, so there is my domain. And then I don't even have to think about the range, because as long as it's a logarithmic function, the range is all real numbers or negative infinity to positive infinity, just depending on how they ask for it. Okay? There we go. All right. So I want to talk to you a little bit about this one, because I actually am going to do this in Pearson because it's a lot easier in Pearson than it is on paper. So for this one, I want you to cross out example 8, and I just want you to say C problem number 21 in Pearson. And I'm actually going to pull it up for you and work it for you now. It is so simple. So this says graph f of x equals 1/3 to the x, and f inverse of x equals log base 1/3 to the x on the same Cartesian plane. It is incredibly difficult to do it on paper, so I'm just going to show you how to do it in Pearson. And normally I wouldn't do this, but the thing is, you can come back and like view this video over and over again, like even while you're doing your homework. So I feel like this is more beneficial to you than me trying to do it on paper. So this homework is titled the same as the notes. So here it is, logarithmic function properties and graphs. It's due on the 19th, Wednesday the 19th. So I think it's example 21 or problem 21. Yeah, perfect. Okay, so it's the exact same question that I have in the notes. Literally the only difference is that I did, I guess, 1/3 in the notes and they did 1/6 here. But I'm going to walk you through how to do this, because even if I taught you how to do it on paper, I don't think that it would translate well to how to do it in here. So I want to show you on here. So basically you're graphing both of these functions, the original function and the inverse, on the same coordinate plane. So you click to enlarge. Okay, and then first we want to graph the exponential one. So remember, if you just hover over it, it'll tell you which tool is which. So first we want to graph the exponential function, 1/6 to the x. So I'm going to hover over the one that says exponential function just to make sure I'm clicking the right one. Then I'm going to click it, and I can click literally anywhere on the graph that I want to. And when I do that, this little box is going to pop up. Now, the nice part about this is that this function has not been transformed in any way. There's no reflection over the x-axis, there's no reflection over the y-axis, there's no vertical shift, there's no horizontal shift, and there's no vertical stretch or compression. It's literally just a base of 1/6 raised to the x power. So the only thing that I have to do is come in here and change my base. So you see they have a base of e, so I'm going to back it up and I'm going to press 1/6. So I just did 1/6 or 1 divided by 6 on my keyboard. And then I click save. Okay, so there's the exponential function. It graphed the first one. But remember, I'm supposed to graph both of these functions on the same Cartesian plane. So now I'm going to click to enlarge again, but this time I need to graph the logarithmic function. So I'm going to hover over this tool just to make sure it's the logarithmic tool, and it is, so I'm going to click on it. And then I click literally anywhere I want to, and the same box pops up. And again, I just need to tell it that this is a base of 1/6. So I backspace the E, and then I type 1 divided by 6 on my keyboard and save. Okay, and check answer. That's all you have to do. Very, very simple. So you can rewind that and watch it again if you want to. Let's see. I'm going to show you how to do one like that in a minute. But anyway, I'll do one more for you really quickly. So this is the same problem with 1/7. So basically you're graphing an exponential with 1/7 as the base and a logarithm with 1/7 as the base on the same plane. So to do it quickly, you would click the exponential tool, click anywhere, change the base to 1/7, click save. Exponential is done. Click to enlarge. This time we click, oh, not that one. This time we click the logarithmic tool, click anywhere, change the base to 1/7 and save. Check answer. Okay, so again, me teaching you that on paper wouldn't really translate to how you do it in Pearson. So I wanted to show you in Pearson. But now that we've tackled that, we can move on to the next problem. So we don't have too many left. I think there's 12, 9, 10, 11, and 12. So let's tackle them. Okay, so example 9 says the graph of a logarithmic function is given. Match the graph to its function. Now we know this is going to be a log base 4 of x. How do we know that? We know that it's log base 4 of x, at least the parent function is, right? Y equals log base 4 of x. We know that's the parent function because all of the answer choices have a base 4. Okay, so now we need to remember, y'all remember it's real hard for me to write straight lines on here. Let's see. Oh, mercy. Let's try that again. Okay. Y'all pretend that's straight, okay. Let's remember what the parent function looks like. So the parent function has a horizontal asymptote. I'm going to move it over in a minute. Sorry. Let's see if it'll let me move it over. Yep. Has a horizontal asymptote at x equals 0. All right. And then it goes like this. And it has this key point right here, which is the key point 1, 0. So that's what my parent function looked like. And my question is, what happens to this function here? So how did this function become this function? And in my opinion, I think it was reflected twice. I think it was reflected over the x-axis or y-axis, excuse me, and then it was also reflected over the x-axis. Because a reflection over the y-axis, if I only went over the y-axis, it would look like that, right? But that's not the direction that it's facing in. It looks like it was then flipped again so that it now, if you flip it again, goes like this. And that purple graph is what we have here. And so it looks like it was reflected both over the x-axis and the y-axis. So I asked myself, what does an x-axis reflection look like? Oh, well, an x-axis reflection looks like a negative on the outside. Then I say, all right, what does a y-axis reflection look like? Well, a y-axis reflection looks like a negative on the inside. So my graph is, or should be, negative log base 4 of negative x. that would be the parent function with both an x-axis and a y-axis reflection. And so I look for that answer choice, and then that's just answer choice B. Okay, and you saw a minute ago, because I kind of clicked through a couple on Pearson, that you'll have a lot like that. Okay, so we'll keep going. That was example 9. Let's tackle example 10. So basically, there's two different types of equations that you're going to see when it comes to solving logarithmic equations. So the first type is demonstrated in example A. Okay, this type is where you have log base A of something equals a number. Okay, this is type 1. So this is type 1 of the logarithmic equations you're going to see. And this is the type where you have a log on one side and a number on the other side. If you have this type of equation, then what you want to do is rewrite the equation as an exponential and solve. So if you have this type, you want to rewrite the equation as an exponential and solve. Okay, so that's the type we have, log base 3 of x equals 2. So we're going to go back to what we did in the beginning of the lesson in example 4, where we rewrote logarithms as exponentials and solved the equation. So we did that with a little circle, 3 raised to the 2 set equal to what's inside. So that's 3 squared equals x, which just means that x equals 9. And that's it. That's all you have to do. Now, on logarithms, you do have to make sure that when you plug the 9 back in, you don't get a negative inside of the parentheses, but we wouldn't here because, or inside of the log, I should say, but 9 is positive, so if you plugged it in here, you would have log base 3 of 9, so it would be positive, so you're fine. I'll show you one where you have to throw out an answer, but this is all you'd have to do. If you have any questions, let me know. But let's take a look at another one. So same situation. We still have type 1, where we have a log on the left-hand side and a number on the right-hand side. So we know that we proceed by rewriting it as an exponential and solving. So we'll use our little circle trick to rewrite it as an exponential. 2 raised to what's on the other side of the equal sign, set equal to what's inside. So that's 2 raised to the third power, set equal to 2x plus 1. Okay, well, we know that that's the same thing as 2x plus 1 is equal to 8. 2 to the third is 8. Okay, so then we subtract 1 from both sides. So we get 2x equals 7. And then we divide both sides by 2. So we get x equals 7 over 2. Now what we want to do is check our answer. This is kind of what I was getting at earlier. We want to check our answer by plugging it back into the inside of the log. So check, let's see, let's write it this way. Check by plugging your answer back into the inside of the log. Okay, and the rule is that the inside of the log always has to be positive. So the inside of a log must be positive. Okay. All right, so we are plugging it back into the inside of the log. So the inside of this log is 2x plus 1. So see, you can see right here, that's the inside of this log. And we need to make sure that when we plug this answer back in, we get a positive number. So 2 times 7 over 2 plus 1, the 2's would cancel, so you just get 7 plus 1, and that's 8. 8 is positive, so that's perfect. I can keep it. So my answer is 7 over 2. So you do have to check your answers for log equations. You want to make sure that if you take your answer and plug it back into the inside of the log, then you get a positive number on the inside. Okay, so if you need to see that explanation again, just go back and rewatch it, but we'll keep going. All right, log base x of 49 equals 2. So this is that same type 1 situation. We have not gotten to a type 2 situation yet. We have a logarithm on the left and we have a number on the right. So I'm going to circle it, x raised to the 2 set equal to what's inside. So x raised to the 2 set equal to what's inside. So x squared equals 49. And so I can solve that by taking the square root of both sides. But when I take the square root of both sides, I have to put a plus or minus in the front. So it looks like initially I get two answers. X equals plus or minus 7, because the square root of 49 is 7. So I get x equals negative 7 and 7. So see how x is in the base position? So we couldn't keep the negative 7. We would have to just keep the positive 7. So we would say x equals 7. So if your x is on the inside of the log, it has to be just positive. It can be any positive number. Can't be 0, but it can be positive. And then if your x is in the base position, then x has to be positive, but it can't be 1. So if x is in the base position, okay, then it must be positive. Okay, but it also can't be 1. Which is why we threw out the negative 7, because we couldn't keep that one. Okay, so again, if you need that explanation, just rewind the video. But for now, let's do another example. All right, same situation. We are still on type 1. We have a logarithm on the left and a number on the right. So we are going to rewrite this as an exponential and solve. So we have 5 raised to the negative 3 set equal to what's inside. Okay, so 5 raised to the negative 3 set equal to the inside of the log, which in this case is 125 to the x power. Okay, so we're going back to how do we solve exponentials? Well, we get the bases the same. So I have a base of 5 here, and I have a base of 125 here. But I can rewrite 125 as a base of 5. So 5 raised to the third power, I believe, is 125. Okay, so we could rewrite this as 5 to the negative 3 is equal to 5 to the third raised to the x. But we know that when we raise a power to a power, we multiply. So that's 5 to the negative 3 is equal to 5 to the 3x. Okay, and so we can drop our bases and set our powers equal. So we will have negative 3 equals 3x, and dividing both sides by 3, you get x equals negative 1. Okay, so x equals negative 1 is probably my answer, but I do want to check my answer before I box it. Now remember, x can be in the base position or it can be on the inside of the log. If your x is on the inside of the log, then when you plug it back in, you just have to get a positive number. If x is in the base position, then when you plug it back in, you have to get a positive, but it can't be 1. Now, luckily, my x this time is on the inside of the log, so I have 125 to the x, and that's the inside of the log, and I'm plugging it back into here to make sure that I still get a positive number when I simplify. So 125 to the negative 1 is the same thing as 1 over 125. Now that's a very small fraction, but it is indeed positive, which means that I can keep that answer. So I would have x equals negative 1 as my answer. All right, continuing on, let's look at E. Same situation, log on the left, number on the right. So we're going to rewrite it as an exponential. 4 raised to the 2 set equal to what's inside. So we have, I'm going to write it up here this time, 4 raised to the second power is equal to x squared plus 8. And we know that that's the same thing as x squared plus 8 is equal to 16. Okay, so I'm going to continue to solve this by subtracting 8 from both sides. So I have x squared is equal to 8. Now I know I can get rid of a square by taking the square root of both sides. So I'm going to have the square root of this side, square root of this side, but I got to do plus or minus. So that would give me 2 answers. X equals negative square root of 8 as well as positive square root of 8. Now I am going to have to simplify those answers, but I'm going to check them before I simplify them because I don't want to simplify something that I have to throw out anyway. So I'm going to check this. So first question I ask myself is, where is the x value? Well, the x is, or the x variable, excuse me. This time it's on the inside of the log, and the inside of the log specifically is x squared plus 8. And so I know that if I plug something back into there, it just has to be positive. It can't be 0, it can't be negative, it has to be positive. So I'm going to try plugging in both of these. Well, if I plug in negative square root of 8, negative square root of 8 squared plus 8. Well, negative square root of 8 times negative square root of 8, negative times a negative is a positive, and then the square root cancels. So basically I just get 8 plus 8, which is 16, and that's positive. So I'm allowed to keep the negative square root of 8. Now let me try positive square root of 8. Positive square root of 8 squared plus 8. The square root and the square cancel. I get 8 plus 8, and I also get 16. So when I plugged in negative square root of 8, I got positive 16 on the inside of the log. And when I plugged in positive square root of 8, I also got positive 16 on the inside of the log. So what that means is that I'm able to keep both of these solutions. So your solutions are x equals negative square root of 8 and positive square root of 8. You have 2 solutions. Now, the only thing is Pearson is going to make you simplify those radicals. So we have talked about simplifying radicals in here before. Basically, we learned that to simplify a radical, you need to find 2 factors of that number. So like you ask yourself, what times what is 8? Well, 4 times 2. So the square root of 8 is the same thing as the square root of 4 times the square root of 2, because 4 times 2 is 8. Well, then we know that the square root of 4 is 2, so that's just 2 square root of 2. So apparently, the square root of 8 simplifies to 2 square root of 2. So the more proper way to write our answer, and the way that Pearson wants you to write your answer, is x equals negative 2 root 2 comma 2 root 2, which is just the simplified version of square root of 8. Okay, take a look at that if you need to, but let's go ahead and move on to F. All right, example F. So example F is different because if you look at it, this is not a logarithmic equation. This is an exponential equation. So the way that I solved parts A through E, where I took the logarithmic equation and rewrote it as an exponential equation to solve, that's not going to work. See, in A through E, they gave me a logarithmic, so I rewrote it as an exponential so that I could solve it. Because I know how to solve exponential equations, we learned that in the last lesson. But see here, they give me an exponential equation. Now, typically, we would know how to solve an exponential equation. You solve an exponential equation by writing the bases the same. But take a look at these two bases. The base on the left is E, and the base on the right is 7. There is no way that you can write an E and a 7 as the same base. So we can't proceed like we normally do when solving an exponential equation by writing the bases the same, because the bases literally can't be written the same. So instead, what we have to do is take this exponential equation, since we can't write the bases the same, and rewrite it as a logarithmic equation that we can solve. So remember, we kind of start the same way. We start with log base E. So we're going to do log base E, okay? And it's of what's on the other side of the equal sign. So of 7 is set equal to 3x plus 1. And see, now we've rewritten that original exponential equation as a logarithmic equation. And we can solve that logarithmic equation because the x is now out of the exponent position. Now we know that log base E of 7 can also be written as natural log of 7. So we'll go ahead and write it that way. So we'll say natural log of 7 equals 3x plus 1. And then we're going to solve for x. So I think the first thing I'm going to do is write it as 3x plus 1 is equal to the natural log of 7. And by the way, remember that's ln, not in, natural log. And so then we'll subtract 1 from both sides. So we get 3x is equal to the natural log of 7 minus 1. And then the last step in solving for x is to divide both sides by 3. So we have x equals the natural log of 7 minus 1 divided by 3. And this is our answer. Now, here's the beautiful part about the original equation being an exponential equation and not a logarithmic equation. If your original equation is a logarithmic equation, then you have to check your answer. But if your original equation is an exponential equation, you don't have to check your answer, because the domain of exponentials is negative infinity to infinity, which means that your x can be anything, so you don't have to check it. So that's lovely that we don't have to plug back in natural log of 7 minus 1 over 3. But anyway, if you need to see that one again, go ahead and rewind. But we are going to now look at example G. So we have 2 times 10 raised to the 2 minus x is equal to 5. Now, that is definitely an exponential equation. The base on the left is 10 and the base on the right is 5. I definitely can't write those as the same base, so I'm going to proceed as I did in example F, where I take the exponential equation and rewrite it in its logarithmic form so that I can solve. But before I do that, I need to get the base of 10 by itself on the left-hand side. So I'm going to divide both sides by 2. Now I have 10 raised to the 2 minus x is equal to 5 over 2. So what we really have is a base of 10 on the left and a base of 5 over 2 on the right. But regardless, those cannot be written as the same base, so I need to rewrite this exponential equation as a logarithmic equation in order to continue solving. So I start with this, that's my base, remember? So I have log base 10, then it's of 5 over 2 is equal to whatever the exponent is. So is equal to 2 minus x. Okay, so that's not pretty, but it's definitely something that I can solve. So I'm going to write it as 2 minus x is equal to log base 10 of, oops, 5 over 2. So first thing is I want to subtract this 2 from both sides because I'm trying to get the x by itself. So I have negative x is equal to, now listen, log base 10, you don't have to write the 10. If a log does not have a base written, it's understood to be 10. So we can just say this as log of 5 over 2 minus 2, and we understand the 10 to be there. Again, if a log is written without a base, we just understand the base to be 10. Okay, and then last step, we want to divide everything by negative 1. So that will isolate the x. So we have x equals negative log, if you want to write the base of 10, you totally can, but negative log of 5 over 2 plus 2. Okay, and again, since my original equation was an exponential equation, I don't have to check my answer if I don't want to. I only have to check my answer if the original equation was a logarithm. Okay, so that was a bunch of equations. Hopefully that will help you when you get to your homework. We have 2 more examples to do, so I know this video has been long, but feel free to pause it as much as you want to. Let's head into example 11. So it says find the inverse of the following functions. F of x equals log of 7x. Okay, well we know how to find the inverse now. Let's practice it. So this is example 1, or I'm sorry, this is step 1 for part A. So we have f of x equals log of 7x. So just like we learned in our inverse lesson, we're going to take the same 4 steps. So y equals log of 7x. Now remember, next step is going to be to switch x and y. So step 1, write it with a y. Step 2, switch x and y. X equals log of 7y. Okay, now step 3 is to solve for y, and that's what I'm going to try to do now. So we have x equals log of 7y. Now what we talked about a second ago is that if a logarithm does not have a base written, we assume or understand that that is a base of 10. So what I'm going to do here is rewrite this logarithmic equation, x equals log base 10 of 7y, as an exponential equation so that I can get the y out from the inside of the log. So 10 raised to the x, we always start with the base. 10 raised to the x set equal to what's inside. So the equivalent form of this equation in exponential language would be 10 raised to the x is equal to 7y, which we know is the same thing as 7y equals 10 raised to the x. And remember, my goal of step 3 is just to solve for y. So the only thing that I have left to do is divide both sides by 7. So I have y equals 10 raised to the x over 7. So it just said to find the inverse. So for my final answer, which is step 4, I'll write that with inverse notation. So f inverse of x is equal to 10 raised to the x over 7. And this is what you would put into Pearson as your answer. So same 4 steps, but we had to learn about logarithms in order to do step 3, which is solving for y. So let's see it again in example 11b, and then we're going to bounce back to example 2 and finish up finding that inverse. Because if you'll remember, we tried to do that in the beginning of the lesson, and we got stuck because we hadn't learned about logarithms yet. Okay, so let's look at this one. We have f of x equals -3 plus the natural log of x minus 2. Step 1, write it with a y. Y equals -3 plus the natural log of x minus 2. Step 2, switch x and y. Okay, x equals -3 plus the natural log of y minus 2. Step 3, solve for y. You see, it doesn't matter what type of function they give you, you always find the inverse the same way. Write it with a y, switch x and y, solve for y. Always the same 3 steps. So let's try to solve for y here. We have x equals -3 plus the natural log of y minus 2. So the first thing I realize is that I'm not going to be able to rewrite this logarithmic equation as an exponential equation until I add 3 to both sides. Okay, so this is now x plus 3 is equal to the natural log of y minus 2. Also, if I'm going to rewrite this as an exponential, I need to be able to see the base. And when it's written as natural log, I can't see the base. But what I know from earlier in the lesson is that natural log is the same thing as log base e. So x plus 3 is equal to log base e of y minus 2. Now I can rewrite it as an exponential. Anytime we're rewriting from log to exponential or exponential to log, we always start the same way, and that's by starting with the base. So it's going to be e raised to the other side of the equal sign set equal to what's inside. Okay, so that would be, let's see, e raised to the x plus 3 is equal to y minus 2, which we can rewrite as y minus 2 is equal to e raised to the x plus 3. So then we're just going to add 2 to both sides. So we get y equals e raised to the x plus 3 plus 2. Okay, so e raised to the x plus 3 plus 2. And that is our inverse. So we would say that our answer for this one is f inverse of x is equal to e raised to the x plus 3 plus 2. And this, of course, is the answer that you would put into Pearson. So now that we know how to take the inverse of logarithmic functions, let's jump way back up here to example 2. Let's see. It was farther than this. Yep, here it was. So remember, we tried to do this earlier, but we had not learned enough about logarithms to be able to finish it. So we were given the function f of x equals 2 to the x, and we were asked to find the inverse. So we began with our 4 basic steps. Step 1, rewrite it as a y. Y equals 2 to the x. Done. Easy. Step 2, switch x and y. X equals 2 to the y. Done. The part that we got stuck on was the solving for y, because we didn't know enough about logarithms yet, but now we can do that. So we have x equals 2 to the y, and we know that that can be rewritten as a logarithm. So we know when we want to rewrite something as a logarithm, we start with the base. Okay, so that it would be like, oops, sorry, I forgot the log. That's helpful. It would be log base 2, okay, then it's of x is equal to y. So we have y equals log base 2 of x. So the inverse that we were looking for, which this is step 4, writing it with, inverse notation or whatever, is f inverse of x is equal to log base 2 of x. And that's what we were unable to do previously because we didn't have enough information. Okay, so this is your answer to this one. All right, and now let's go tackle example 12, which will finish out this lesson. So the thing that I love about example 12 is it actually kind of brings together everything from the last two lessons. So I really want you to pay attention closely to example 12, because if you can do example 12, then you have mastered everything in this lesson, which was logarithmic function properties and graphs, as well as everything in the last lesson, which was exponential function properties and graphs. So it's really important. Okay, so it says use the function f of x equals -4 plus log base 3 of x minus 4 to answer parts A through F. So part A says find the domain of f. That's easy. F is a logarithmic function. Earlier in this lesson, we wrote a rule that said to find the domain of a logarithmic function, you take the inside of that logarithmic function and you set it greater than 0. So the inside of this logarithmic function is x minus 4. So I'm going to say x minus 4 is greater than 0. Adding 4 to both sides, I get that x is greater than 4. So if they asked me for this in set builder notation, I would say x such that x is greater than 4. And if they asked for this in interval notation, I would simply say 4 to infinity. Okay, part A is done. Let's see what they ask me for in part B. So part B says choose the correct graph. Now I'm going to graph this with transformations. So I'm going to rewrite the function for you. Okay, the original function was f of x is equal to -4 plus log base 3 of x minus 4. So this -4 here on the inside of the parentheses indicates to me that it was shifted to the right 4. And this -4 here on the outside of the parentheses indicates to me that it was shifted down 4. Now, remember what the parent graph for a logarithm looks like. Whew. Y'all know it's not easy to write on this thing. Here we go. Okay. Y'all pretend like that's super straight. There we go. Okay, so we know that our parent function has an asymptote at the y-axis, or x equals 0. And we know that it goes like this, right? And it goes through this point right here, which is the point 1, 0. Okay, so that's our parent function. Which of these looks like the parent function that I have drawn here, shifted to the right 4 and down 4? So take that blue graph and shift it to the right 4 and down 4. Well, to me, there's only one answer, and it's pretty obvious. It's got to be A. Okay, so we're going to save that. All right, and we are going to go on to the next one. Now it says from the graph, give the range and any asymptotes. Well, we already know the domain because we found it in part A. The domain was 4 to infinity. That's why they're not asking us for that. Now, the range is a trick question, to be honest with you, because we know that the range for every single logarithmic function that has ever existed is -infinity to +infinity, or all real numbers. So there's our first answer. Then they want to know if there were any asymptotes. Well, let's go back and look at our graph. You see, the original graph, or the parent function, has an asymptote at x equals 0. So that asymptote is going to move with the function if I shift to the left or to the right. So if the asymptote used to be here at x equals 0, and I shifted it to the right 4 units, then it's now at x equals 4. So I have a vertical asymptote at x equals 4. Okay, so those are my two answers. That's all they wanted for part C. Now let's see what they're asking me for in part D. Okay, part D says find the inverse of f. So I'm going to remind you what f is so we don't have to keep flipping back, just copying it from the top of the notes. F of x equals -4 plus log base 3 of x minus 4. So I'm going to start my inverse process. Number one, write it as a y. Y equals -4 plus log base 3 of x minus 4. Step 2, switch x and y. X equals -4 plus log base 3 of y minus 4. Okay, step 3, we're solving for y. So I'm going to rewrite it. And I'm going to start trying to solve for or isolate this y value right here. Okay, so I think the first thing I'm going to do is add 4 to both sides so that at least the logarithm is by itself on the right-hand side. So we would have x plus 4 is equal to, this would cancel, log base 3 of y minus 4. Now I know that my job is to solve for y, and that the only way that I can get that y out of the inside of the log is to rewrite this logarithmic equation as an exponential equation. So I always start with my base. Remember, it's 3 raised to what's on the other side of the equal sign, set equal to what's inside. Now I can solve it. I've got 3 raised to the x plus 4 equals y. Okay, so that's, or equals y minus 4, excuse me. So that's y minus 4 is equal to 3 to the x plus 4. So I've almost solved for y. The only thing I need to do is add 4 to both sides. So I'm going to get y equals 3 to the x plus 4 plus 4. And there's my inverse. That's what they were asking for in this part, which is part D. F inverse of x is equal to 3 raised to the x plus 4 plus 4. Okay. Now let's see what they're asking me for in the next part. Okay, find the domain and range of F inverse. That's a trick question. Absolutely not. Because I have already found the domain and range of the original. Go back and look. You found the domain of the original, where was it? Here it is. You found the domain of the original in part A. The domain of the original was 4 to infinity. Okay, so I'm going to go here and say, wait a minute, the domain of the original was 4 to infinity. And then in part C, you found the range of the original. It was -infinity to infinity. Okay. So I don't need to find domain and range again for my inverse, because I know the rule that in inverses, just like x and y switch places, so do domain and range. So that means that the domain of the inverse is going to be -infinity to infinity, and the range of the inverse is going to be 4 to infinity. Okay, so this is the answer that they're looking for in part E. All right, and here's my very last part. They are asking me to sketch the graph of f. So let's use our transformations again. Remember, or they're asking me to sketch f inverse, excuse me. F inverse is 3 to the x plus 4 plus 4, right? So that means the parent function would have been y equals 3 to the x. And we know that the parent function for exponentials looks like this. We know that it goes through the key point 0, 1. And we know that it has a horizontal asymptote at y equals 0 because we have that parent function memorized. Now, this plus 4 up here tells me that it's going to the left 4, and this plus 4 here tells me that it's going up 4. So I need to take this graph right here, and I need to shift it to the left 4 and up 4. So if I had to pick one of these that looked like it was shifted to the left 4 and up 4, I think that would definitely be D. And that is the answer. All right, so that was a particularly long lesson, but I hope that you paused it as many times as you needed to take a brain break. Just remember that you'll have to upload these guided notes to the link that I will provide in Moodle by 11:59 p.m. on Tuesday, April the 18th. And if you have any questions, of course, you can see me after class. You can email me, or you can come see me during my office hours, or you can go see the tutors in Fayard 309. So if you guys have any questions, let me know. But otherwise, we will pick up with the next lesson on Tuesday, which is the 18th, and it's entitled Properties of Logarithms. Believe it or not, we only have 3 weeks of classes left in the semester and then finals. I'll see you guys on Tuesday.